Okay, let's dive back in. Last time we took a really good look at the economic side of sustainability, didn't we? Focusing on things like life cycle cost analysis.
Yeah, LCCA. That's a really mature methodology, decades old.
Totally. People pretty much know the drill with that one. Very established.
Exactly. There's a solid structure, decades of practice behind it.
Right. But today, we're shifting gears. We're looking at a pillar that, wow, it feels like it's been accelerating like crazy, especially these last, what, 5, 10 years maybe?
Oh, absolutely. The environmental pillar.
Yeah, the environmental one. It's gone from being, important to just front and center in so many conversations.
It really has. The urgency around environmental impact has just shot up. So tools to actually measure and understand that impact are becoming, well, essential,
Hmm.
especially in fields like civil engineering.
And the main tool here, kind of the environmental cousin to LCCA, is the life cycle assessment, or LCA.
Hmm.
Think of it as the big environmental audit for a product or even a process. Looks at the whole picture, start to finish.
That's a good way to put it. It's a systematic approach to quantify, and that's the key word, quantify the environmental flows, what goes in, what comes out across the entire life cycle.
Okay, but LCAs, they don't usually just float around on their own, do they? Your sources pointed out they're part of a sequence.
That's right. Typically, yeah.
The LCA gives you the data. That data then informs something called a product category rule, a PCR. And then those two together let you create an environmental product declaration, the EPD.
Exactly that sequence.
Yeah.
LCA gathers the info, the PCR sets the specific rules for how you present that info for, say, concrete versus steel, and then the EPD is the final document, the public one, that shares the results.
Gotcha. So that's what we're doing in this deep dive. We're going to unpack these core ideas, LCA, PCR, EPD, figure out what they are, how they link up.
Mm-hmm.
And we'll also touch on a few other ways to look at environmental impact that your sources mentioned. Basically, trying to give you a good handle on this complex area using the material you shared.
Sounds good. Let's get into it.
Okay, so the LCA itself, where does it start? Our sources point to the ISO standards, right? The 14E40 series.
Yeah, those ISO standards are fundamental. They define an LCA as a technique for assessing the environmental aspects and the potential impacts associated with a product or system. Crucially, it's about quantifying those impacts, turning descriptions into numbers.
Right, quantification. So it's not just saying it has an impact, but it has this much impact. And how does that process work? The standards lay out specific steps, don't they?
They do. You can think of it as a multi-stage process. First, you define the goal and scope. That's critical.
Okay.
Then you do the inventory analysis, the life cycle inventory, or LCI. That's collecting all the data.
Right.
After that comes the impact assessment, life cycle impact assessment, LCIA, where you figure out what that data means environmentally.
Uh-huh.
Then you interpret the results. Often there's a critical review step. And finally, reporting.
Okay, let's take that first one, goal and scope definition. Why is getting that right at the beginning so vital?
Oh, because it sets the stage for everything else. The goal defines why you're even doing the LCA. What question are you trying to answer? Who's it for?
Makes sense.
And the scope defines what exactly you're studying. The specific product, the system boundaries where you start and stop counting, and, really importantly, the functional unit.
The functional unit, that sounds key. What is that exactly?
It's the basis for comparison.
Yeah.
It defines the function the product delivers. So if you're comparing, say, different wall insulation types,
Okay.
the functional unit isn't just 1 pound of insulation. It might be something like providing X amount of thermal resistance over a 50-year building life.
Ah, so it's about the job it does, not just the amount of stuff.
Precisely. Everything in the LCA gets scaled back to delivering that specific function. That allows for a fair comparison between different solutions that achieve the same end.
That makes a lot of sense. And the scope also sets the system boundary. You mentioned that. That's where we get those terms like cradle to gate.
Exactly. Those terms define which life cycle stages are actually included in your analysis.
Okay.
So cradle to gate, that's usually looking at the early stages. Module A1, raw material supply, getting stuff out of the ground. A2, transport to the factory. And A3, the actual manufacturing.
So from the cradle of the raw material up to the factory gate when the product leaves.
You got it. It stops before it gets shipped to the construction site or the store.
Right. And cradle to grave takes it further.
It does. It includes everything in cradle to gate, plus the transport to the site, the construction or installation phase, that's modules A4, A5, the whole use stage, B1 through B7, think maintenance, repairs, energy use during operation.
Okay, the middle part of its life.
And then all the way through the end of life stage, C1, C4. That's demolition, transport to waste facilities, processing, and final disposal to the grave, like landfill.
Got it. Covers the whole lifespan until it's basically gone.
Right.
And then there's cradle to cradle. That's the more circular idea. Adds another piece.
Yes, that brings in Module D. So it's A1 through C, covering the whole life up to disposal. But then Module D looks at the potential benefits or burdens that happen beyond the system boundary.
Like recycling or reuse.
Exactly. When materials get reused, recycled, or maybe energy is recovered from waste, those benefits get accounted for in Module D, sort of looping back.
Okay, so A is production construction, B is use, C is end of life, and D is that beyond loop for circularity. And being super clear in the scope about which modules you're including is obviously crucial.
Absolutely critical. It determines what impacts you're measuring and what claims you can ultimately make based on the LCA. Transparency is key.
Okay, so that's the setup. What's next? The Life Cycle Inventory LCI.
Right, the LCI. If the goal and scope was planning the audit, the LCI is the actual legwork, the data collection.
Ah, this sounds like the hard part.
It often is. You're basically creating a massive detailed list of everything that flows into the system and everything that flows out of it at every single stage you define in your scope.
So inputs like energy used, raw materials consumed, water.
All of that quantified. Kilograms of steel, megajoules of electricity, cubic meters of water.
And outputs. That's the product itself, but also.
Also, any co-products made alongside it. Any waste, generated solid waste, hazardous waste, and, critically, all the emissions. Things released to the air, to water, or to the soil.
So you're counting up tons of CO2, liters of wastewater, kilograms of particulate matter, all tied to specific processes.
Exactly. And getting accurate, reliable data for all of that. That can be the most resource-intensive part of the whole LCA. It takes time and effort.
I can imagine. Okay, so you've gathered this mountain of raw data in the LCI. Then comes the Life Cycle Impact Assessment, LCIA. What happens here?
This is where the magic, or maybe the translation, happens. You take all those raw inventory numbers, the kilograms of this chemical, the joules of that energy, and you translate them into potential environmental impacts. Because just knowing you released, say, 5 kilograms of nitrogen oxides doesn't immediately tell you the environmental consequence.
Right, it's just a number.
But the LCIA connects that number to potential problems like smog formation or contributing to acid rain. It makes the data meaningful in terms of environmental or human health effects.
Okay. And your sources mention some key impact categories that LCAs typically look at.
They did. Common ones include things like greenhouse gas emissions, obviously linked to climate change, smog formation potential, eutrophication potential, that's nutrient enrichment in water bodies, ozone depletion potential, ocean acidification, and they specifically mentioned global warming potential, GWP.
Yeah, let's pause on GWP for a second, because the sources really highlighted how different gases have dramatically different impacts here.
It's a crucial concept. GWP measures how much heat a greenhouse gas traps in the atmosphere over a specific time period, usually 100 years, compared to the same mass of carbon dioxide, QO.
So QO is the baseline, GWP of...
Exactly. QO is a 1. But then you look at methane, CHA, it has a much higher GWP, especially over shorter time frames, like 20 years, though it breaks down faster than CO. Nitrous oxide, NUO, is also significantly higher.
But the one that really stood out in the sources was sulfur hexafluoride, SF-Euro. The numbers there were.
Wow, they're staggering, aren't they? SF-Euro has a GWP of over 22,000 times that of CO-Euro over 100 years.
22,000.
Yes. So releasing just 1 kilogram of SF-Euro has the same warming impact as releasing over 22 tons of CO.
That's incredible. It really shows why you need this LCIA step. Just looking at the massive emissions in the LCI wouldn't tell you this story.
Precisely. The LCIA reveals the relative potency of different substances.
Okay, so the LCIA gives you these potential impact scores.
Right.
What's the next step in the LCA process?
That would be element 4, life cycle interpretation. This is where you synthesize everything.
They're throwing it all together?
Yeah, you analyze the results from the LCI and LCIA. You identify which life cycle stages or specific processes are causing the biggest impacts, the hotspots. You also check how sensitive your results are to the assumptions you made, evaluate the completeness and consistency, and then you draw conclusions based on the original goal and scope you set. And importantly, you state the limitations of the study.
Right, being clear about what the study can and can't tell you. And then there's a review.
Yes, the critical review. The level of scrutiny depends on how the LCA will be used.
How so?
Well, if you plan to make a public claim comparing your product to a competitor's, like saying product A is greener than product B, the ISO standards require a rigorous third-party review.
by independent experts.
Exactly. A panel of external experts reviews the study to ensure it's sound, and their comments usually have to be made public. For internal studies, maybe just for process improvement, a less formal internal review might be enough.
Got it. And the final piece is reporting.
Right. You compile a comprehensive report detailing everything.
Hmm.
The goal, the scope, the LCI data, the LCIA results, the interpretation, the review process, limitations, all laid out according to the ISO guidelines. Sometimes the EPD itself serves as the main public report summarizing this.
Okay, that gives us a solid understanding of the LCA process itself, but you mentioned that sequence. LCA feeds into the PCR, which feeds into the EPD. Let's talk about PCR's product category rules.
Right, so the LCA gives you the environmental data based on general ISO rules, but different products are made differently, used differently.
Sure, concrete isn't made like steel.
Exactly. So the PCR provides the specific rules, like a detailed recipe book for how to conduct the LCA and report the results in an EPD for a specific type of product.
Ah, so there's a PCR for concrete, a different one for structural steel, another for insulation, maybe?
Precisely. ISO calls PCRs a set of specific rules, requirements, and guidelines for developing Type 3 environmental declarations, that's EPDs, for one or more product categories.
And the point is consistency.
Yes. They ensure that if two different companies make, say, concrete, and they both follow the concrete PCR, their resulting EPDs should be comparable because they use the same methodology, same assumptions, same impact assessment methods, defined functional unit, etc. It enables intra-category comparison.
Okay. And these PCRs themselves have to follow standards.
They do. Standards like ISO 20930 guide PCR development. A PCR will specify things like exactly which products are covered, which life cycle stages must be included. Example, must it be cradle to gate or cradle to grave? Specific rules for data collection and impact calculations. What information has to be in the EPD?
Sounds quite detailed.
Oh, it is. And they also specify how long the PCR itself is valid, typically around 5 years.
5 years? That's not very long.
Well, it reflects how quickly technology, materials, and even our understanding of environmental impacts can change. They need regular updates to stay relevant.
Good point. And PCRs also need a review.
Absolutely. A third-party panel of experts has to review a draft PCR. Often there's a public comment period, too, to make sure it's scientifically sound and practical for the industry it covers.
Okay, so you do your LCA, carefully following the rules laid out in the specific PCR for your product type. Now you're ready to create the EPD, the Environmental Product Declaration.
Exactly. The EPD is the final document. It's designed to transparently communicate the environmental performance of that product based on that LCA conducted according to that PCR.
You called it a nutrition label earlier. I like that analogy.
It aims to be like that. Standardized information, clear format. ISO 14025 lays out the objectives. Provide objective LCA-based data, help people make informed comparisons, drive environmental improvements by making performance visible, and supply data for broader environmental assessments, like at the building level.
Okay, but there's a catch, right? Your sources highlighted a really important caveat about that informed comparison part. Where does the nutrition label analogy break down a bit?
This is absolutely crucial to understand. ISO is very clear. EPDs developed using different PCRs or under different EPD program operators may not be comparable.
So even if two products seem similar or do the same job.
Right. While EPDs allow comparison within the same product category if they follow the exact same PCR, like comparing two concrete mixes under the concrete PCR.
Okay.
You generally cannot reliably compare an EPD for, say, concrete using the concrete PCR directly against an EPD for steel using the steel PCR, even if both could be used for the same bridge component.
Why not?
Because the underlying rules, the scope definitions, the background data, the specific impact assessment choices made when developing those different PCRs might not align perfectly. Comparing them directly could be misleading, like comparing apples and oranges based on nutritional labels that use different serving sizes or analysis methods.
Wow, okay. That's a really key takeaway. EPDs are great for comparing options within a specific product category following the same rules, but comparing across categories or different rule sets is tricky.
It requires real caution and expertise to do meaningfully, if at all, based solely on the EPDs.
Your sources included an example looking at a steel EPD.
Yeah, the North American PCR for designated steel construction products. That's a good example of a specific rule set. Covers various steel product types developed with industry input.
And the sample EPD based on that PCR for fabricated hot-rolled structural sections, what did it show?
Well, it clearly stated the basics. It was based on that specific PCR. It was a cradle-to-gate analysis, modules A1, A3, and the declared unit was 1 metric ton of fabricated steel.
Okay.
And the core information was in the table showing the LCIA results, the potential impacts, like GWP, acidification potential, eutrophication potential, smog potential,
Hmm.
all calculated per metric ton of that steel product.
Just the numbers.
Yes. But importantly, good EPDs often break down those impacts by life cycle module, often using charts.
Right, showing where the impacts actually happen.
And in that steel example, the charts made it really obvious. The vast majority of the environmental footprint, something like over 80% for most impact categories, was concentrated way back in Module A1.
A1, that was the initial production of the steel at the mill, right?
Exactly, producing the raw steel itself. Then, if you zoomed into just the fabrication stage, A3, the biggest chunk of that impact came from energy consumption during fabrication.
So the EPD clearly pinpoints the hotspots.
Precisely. It tells you if you want to make steel greener, the biggest leverage point is tackling the steel mill's process and maybe the energy used in fabrication.
That makes the data really actionable for manufacturers.
It does. It shows where R&D, process improvements, or switching to cleaner energy will give you the biggest environmental bang for your buck.
So these EPDs, built on LCAs and PCRs, they're not just academic exercises. They're becoming really important in practice.
Absolutely. This is where, as they say, the rubber meets the road. We're seeing major purchasers start to require them.
Like who?
Well, a big one is Caltrans, the California Department of Transportation. They now require EPDs for certain materials used in state projects, things like structural steel, reinforcing bar, concrete, asphalt.
And California's decisions tend to ripple outwards, don't they?
They often do. It sends a strong signal. And it's not just states. The federal government, through the General Services Administration, GSA, they manage federal buildings and procurement.
Okay.
They're also moving this way. Under the Inflation Reduction Act, the IRA, they're setting up requirements for low-embodied carbon materials. They're establishing GWP limits for concrete and asphalt used in their projects.
So they'll look at the GWP value on the EPD and say, we want bids using materials below this threshold.
Essentially, yes. They aim to procure materials that are in the lower range of reported GWPs, pushing the market towards lower carbon options.
That's a significant driver for change.
It is. Though, it's worth noting, as the sources point out, that a product's GWP can sometimes be influenced by things like the electricity grid mix powering the factory, which isn't always directly controllable by the manufacturer. There are nuances.
Still, the trend is clear. This whole area is moving incredibly fast. Your sources mentioned that just a few years back, EPDs were pretty niche, and now they're underpinning major regulations.
The pace of change is remarkable. Europe has generally been ahead on implementing these systems, developing PCRs and databases, but the U.S. is catching up quickly, especially with recent policy pushes.
So for anyone listening, staying updated is key.
Definitely. You really need to keep an eye on the specific regulations and requirements emerging in your sector or region.
Okay, so we've covered the main toolkit, LCA for the data, PCR for the rules, EPD for the communication. But your sources also mentioned some other frameworks for thinking about environmental impact, looking beyond just one product's life cycle.
That's right. While LCA and EPDs are powerful for product-level assessment, these other frameworks offer different perspectives, often at a broader scale.
Like the ecological footprint, what's that about?
The ecological footprint isn't tied to a specific product. It's more about overall consumption. It measures how much biologically productive land and water area a population or an individual needs to produce all the resources they consume and absorb the waste they generate.
So it asks, how much of the planet's capacity are we using?
Essentially, yes. It compares human demand against the Earth's available biocapacity.
And the water footprint. Similar idea, but just for water.
Exactly. It focuses solely on freshwater use. It calculates the total volume of freshwater used directly or indirectly to produce the goods and services somebody consumes. And it breaks it down into different water types.
Yeah.
Blue water from rivers, lakes, groundwater, green water, rainwater stored in soil, and gray water, the volume needed to dilute pollutants.
Interesting. And then there was the really big picture one, planetary boundaries.
Right. This framework operates at the global scale. Scientists identified 9 critical Earth system processes, things like climate change, biodiversity loss, land system change, freshwater use, nitrogen and phosphorus flows.
Okay, the major global cycle.
Yes, and for each one, they tried to define a quantitative boundary, a kind of safe operating space for humanity. Crossing these boundaries significantly increases the risk of triggering large-scale, potentially abrupt or irreversible environmental changes.
So While an LCA EPD tells you the impact of this ton of steel,
Hmm.
these other frameworks give you context, like how does our total consumption fit within the planet's limits, ecological footprint, planetary boundaries, or what's the specific pressure on water resources, water footprint?
Precisely. They look at sustainability from different angles and scales, complementing the detailed product focus of LCAs and EPDs.
Okay, so wrapping this up, what does this journey through the environmental pillar mean for you, the listener? We've seen these tools, LCA, PCR, EPD, become central.
Yeah, the EPD really is emerging as that critical nutrition label for environmental impact.
And they're rapidly moving from just being nice to have information to actual requirements, driven by major players like Caltrans and the GSA using things like GWP benchmarks from the IRA.
Definitely. And we've seen the complexity, too, the huge differences in impact potentials, like between Kitosi Euros and SAVR, really highlights why quantification matters.
And that crucial limitation, EPDs aren't always directly comparable if they're based on different rules, different PCRs. That's vital to remember.
Absolutely. It's a fast-evolving field.
Mm.
Europe might be further along in some ways, but the U.S. is definitely in the midst of significant change. Staying informed about your specific context is really important.
Which brings us to a final thought. This whole process, from the detailed LCA inventory all the way to these impact scores on an EPD, it raises a pretty big question, doesn't it?
It does. Given that huge range of impacts we see, think about that SF Euro comparison, and given the real challenges in comparing products across different categories because their EPDs might follow different rules.
Right, even if they perform the same basic function.
Exactly. So the question is, how do we effectively translate all these complex, sometimes non-comparable environmental metrics into practical, actionable decisions? Decisions about projects, about procurement that genuinely move the needle towards, our global sustainability goals.
How do we make sense of it all to make the right choices? Something to mull over as you encounter EPDs and environmental data out there. Thanks for taking this deep dive with us.